now. There's a quiz that you should take online, but it's a Stack and Q quiz. But we've got a limited amount of time, and I should go over the practice exam because, I think you find it helpful. Please turn on the lights back there, somebody. Yeah, there we go. Front light I turn off because, easier to see. So, right. I want the practice exam, not the actual exam, because otherwise I'd have to write a new one, and I don't have time for that. All right, so, right, remember you get a cheat sheet in for this exam, front and back. Don't really care the details about that other than that you got front and back on the cheat sheet. It's going to be a list of stuff over here in case you forget it, right? Dot length for string, dot size. Not going to tell you what it does, but hey, this actually, pretty straightforward as to what they do. Other thing, if it exists in Java, it's perfectly legal to use on the exam. Okay. All right, so first page of the actual exam is going to look pretty much exactly like this page. The only difference is that the exact details of the questions are going to be wrong. I'm not wrong. The exact details of the question are going to be different. So answers are pretty straightforward. Just simply follow the pointers. D.previous.previous.next.previous. That's B. In fact, if you follow all of these through, they all turn out to be. One of the things you can do is that if you see next and previous's cancel each other out, right? So B.next.previous, next, prev. Those cancel, next and prev cancel. They're all B. All of them are B. Write a sequence of commands that will remove the tail of a doubly linked list. Right? For a doubly linked list, that's fairly straightforward. That would be, right? So tail is equal to, so first off, what we want is to we want to remove the tail. So I guess that would be tail dot is equal to tail.prev. Okay, and then what we want to do is say tail.next is equal to head. Well, actually, no, because that's not a circular linked list. Tail is equal to tail.prev. Let's see, what am I missing? And tail.next is equal to null. And that should pretty much fix it, I think. Right? There should be no other pointers pointing to the linked list to the tail at that point. So and using a linked list with 3 nodes, draw what happens to the list once each line executes when you remove the tail. A lot of the actual questions on the exam are going to be, for this one, are going to be a bit different. Instead, on the exam, what I do is I give you some code and I ask you to draw what happens with the code. So draw what happens to a linked list, like with 4 nodes, as this code executes. So I don't have you writing like what is the command to do that. It's more the drawing that I would like to see. And of course, they always take away my markers here because they're evil. Not that I need any. But for here, what I would want to see is basically the steps of like labeling the. Yeah, go ahead and toss. Yeah, something like this would work. Where basically, hey, I've got a list of 3 nodes. Right, here's the tail. Then saying, boom, 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 boom. Right, now this is the tail. And then finally, tail. And then we get rid of this guy over here, so we just simply have, and that guy will be left to get garbage collected in a bit, right? Something like that is perfectly fine, or just showing that basically that crossing this guy out will cross this guy out. That's perfectly fine. So long as you communicate that what's going to happen to the geometry of the list. Okay. Similarly with when we're adding nodes to a linked list. Although on the exam, I think we're dealing with more of a thing that happens when you are adding and then, when you're removing nodes from a linked list. So what I'm more interested in doing is the code for you, because that is a bit more hard to figure out. Well, this one isn't too bad. First two questions are going to be similar to this. They are going to be basically stuff that you would expect to see on the second homework. Let's see. So over here, right, give me the minimum and the maximum value stored in the linked list and return their sum. It's not that hard, right? Especially since it's a linked list of integers. The reason I've declared it like this is that we can assume that basically anything in the list is that the smallest thing in the list is going to be smaller than the biggest integer, and the biggest thing in the list is going to be bigger than the smallest possible value, right? Another thing you could totally do, by the way, though, if you were writing this from scratch, is to say list.get 0. Notice also I don't specify whether or not these are linked lists or array lists, although you can assume they're array lists, but I don't specify. So this was a perfectly fine way to start this as well. Okay. So how do we solve this? I like to use a fairly simple for each loop but there's there's plenty of ways to solve this. For num in list. Sorry, Python. Been working in Python too much. If num is greater than the max, then congratulations, we found the new maximum. Is it not?
Like integer num instead of int num.
Oh no, autoboxing handles that perfectly fine. For max, the max is equal to num. So int will work right there just fine, as would integer, because Java automatically converts from int to integer. And then similarly, all you got to do is, if it's less than the minimum, then that's the new minimum. Yes?
Is that why you can use the greater than and less than symbols too?
Yes.
Rather than using comparisons because they're objects?
Yep. It's a built-in feature in Java that you can treat capital D doubles as doubles. You can treat integers as ints. You can treat characters as chars. But you cannot mix and match a char and an integer. Those won't. Even though you could totally mix and match ints and characters, you can't do that. Same with doubles, capital D doubles and ints. That causes some issues. Okay. And then it's got the return statement already created, which is just return min plus max. The time complexity of this algorithm, well, the way I wrote it will be O of n regardless of whether it's a linked list or an array list. You can assume that these are array lists, but because I'm using the iterator, you can assume that it's going to be a O of n, even with a linked list, because with a linked list, you use the iterator function and goes through it in O of n time. It just simply follows the pointers. If, on the other hand, you do for int I, index is equal, for int I, and then go through the indices and use the get method, with an array list, it would be O of n. With a linked list, this would be n squared, because each get operation is O of n time. Reverse words. Suppose you have some list of strings. Write a method, reverse words, that returns a new list with all the strings reversed in it. Okay. So, reverse word. Just making sure that's all right. So what we need here again is we need a new list. So list string output is equal to new, and it's important that you declare some kind of list here, be it array list or linked list. You can't say new list. That's a mistake.
How are you allowed to do that for the problem?
What?
Like, I don't understand how you're allowed to do that. Like, it says returns a list, and you're changing it then to a specific.
So a specific type of list. That's perfectly fine. So you can always store a more specific version in the more generic container. Think of this as a...
No. I understand like how that's legal what you did, but I don't understand how that solves the problem. Because you're returning a specific list, but like your function only declares that you return a list.
Yes, any kind of list.
But then what? Like if I was using that function or that method, sorry, like, and I was expecting like a generic list, and I want to go to.
You can't get a generic list back is the thing.
Okay, but I could be expecting to get back a linked list if I passed in a linked list. Yours would always return an array list.
Right. Now, you'd have to look. That would be the case where I'd have to put that in the documentation with what I'm returning.
So why wouldn't you write array list in your thing?
In this one,
Yeah.
because it's easier to read on an exam.
But it's not the same function then. Like
If I did return array list, then it would always return an array list, and that'd be perfectly fine. But the reason I have a list here is also because I want to make sure, because I don't want to give you any hint there that what you're supposed on the practice exam that you're not supposed to do this.
But you can solve the problem without even writing that line of code.
This one?
Yeah.
Well, you need a new list.
You don't. It says like,
Returns a new list with all the strings reversed.
but I could add, so I could take like my current list that you passed in.
Yes, and you could modify it and swap out everything. But I'm saying for the parameters of the problem I set up, it's specifically done so that there's this trap of writing this. There's a pedagogical, a teaching reason for it, as opposed to a really good programming reason for it, right? And I sometimes have to make that decision there. Ideally, though, right, I should be saying that, yes, I should be more specific about what type of stuff I'm returning, right? But also there's the idea sometimes you just don't care. For most parts, lists are lists, and so long as you're just iterating through a list, it doesn't really matter in terms of performance. But, I mean, it's a good point. Did I answer your question or no?
Yeah, but like I just don't see how like that solves the problem. Like if I have a method that returns a generic list, and now you're returning a specific
Type of-
list, that's not returning a generic list.
I mean, this is returning a list. It's returning a list object. An array list is a list. Via inheritance.
I understand what you're saying, but I don't. There, that's fine.
Okay, I can talk to you more about it later. It's just one of those quirks of Java that you can do, especially with the whole inheritance thing. So anyway, so let's go ahead. So what we need to do is now go through the list. I'm going to go through and say string word in list. I'm really a fan of the for each loop when I can use them. For string in list, and now I have to reverse each string and add it to my list. So easiest way to reverse a string is to like use a string builder method, but you might not know how to use a string builder, so that's fine. So instead what I do is string reversed is equal to an empty string, and I just basically write an accumulator there. And what I do is that I simply say, and I'm going to use another for each loop over here, for car c in word dot get car array, or is it to car array? It's to car array. Working off of memory here. Change it to character array. Right now, if I did this, reversed is equal to reversed plus c, that would tack each character onto the end of it, and so I'd end up with the same thing that I started. But I could just simply, but if I swap it around, it's actually pretty cool. then now it's reversed. And I get to use a for each loop again. Or I can just write a for loop that goes backwards through it and concatenates it. But, you know, I can be snazzy like this when I'm writing it. And so now that it's reversed, output.add reversed. And that adds everything reversed. The time depends on whether you're judging this by characters or strings. If you're judging it by strings, we had to reverse each string once. There were n strings to reverse, so it takes O(n) time. Similarly, if you're judging by characters, we have to go through each character once. So, again, it's O(n) time. Most of the answers are going to be either O(n) or over n squared. All right. Write a method called delete list, which removes all items from a list, making it empty. There's a couple ways to do this. One is to have a while loop. While head is not equal to. So while head is not equal to. Is not equal to null. Head is equal to head.next. Actually, yeah, head is equal to head.next, and that just simply deletes the head each time. And then we're removing a node, so we'd want to do size minus minus. And then another thing we could do is do tail is equal to null over here if there's a tail. Yes?
Is this a doubly linked list?
If it's a doubly linked list, the node objects are doubly linked, see here. So boo. Head is equal to head.next. Head.previous is equal to null. Boom. Now it works for doubly linked lists. Okay. Alternatively. Oh yeah. Well, head is null. This stops once head is null.
Yeah, because you just do head null, tail null, size 0.
Although this would actually hit a null pointer exception once I hit, once I get to the last item, right? And let's see, is there a tail in this? Tail's optional. While head is not equal to tail. There we go. So that way it stops there. Honestly, though, there's a much easier way to do all this, to be honest, which is the following. Head is equal to null. Tail is equal to null. Size is 0, which is the last important thing. Because otherwise, your list is going to get very, very confused as to what indexes are valid. And when your list gets confused, it's error. That's why it's worth 3 points, because it's not particularly difficult. Here's another method. Write an instance method called count. Count iterates over a linked list and returns the number of items that occurs in a linked list. By the way, on the exam, we're only dealing with singly linked lists. Everything is singly linked list on the exam. This is, again, you can access tail. Tail is optional here. There's no need. So what we're doing is we're counting the instances of a specific item. So what we do over here is that we use current. And basically what we do is that we're just going to iterate forward using a while loop until we hit the appropriate location. Current is equal to head. While current is not equal to null, and I can do this one as not equal to null because I'm not trying to do anything when I'm advancing after advance. So and then I'll do current is equal to current.next down here because that's essentially the equivalent of doing I++ for this. Okay. Yep. Int. And then we need an int count. Just going to point out, I haven't looked at this since last year. so I'm kind of working off of So again, this is like the first time I've seen these problems in like since the respective time last semester. Which should also emphasize that these problems aren't that hard once you really understand linked lists. Okay, count is equal to 0. We're going to count, and basically what we're going to do is we're going to check each item. One of the key mistakes that you do not want to make is go, hey, if current equals item. Don't do this. I don't like this very much. It makes me very, very sad whenever I see something like this, which is when you confuse the item for the node, right? Don't confuse the data for the node. What we're trying to do is current.item is equal to item. If you put current.data instead, I don't care, right? I don't really call it item, call it data. It's fine. Yes.
Can you use the equals or should you use dot equals?
Dot equals probably is better. So again, I've been working a lot in Python, and so it's been kind of just, oh yeah, dot equals is a thing in Java. Okay, but honestly, on an exam, I'm just gonna say, okay, whatever, because on an exam, I'm looking for your problem-solving capabilities, not for the minor syntactical things. Okay. So if the current item equals the item, then guess what? Count plus plus. So that's this problem done. That was an easy 10 points. Now what's cool is that actually you notice that we also have to figure out what the big O notation is. Well, we're going through once through each item, right? And how do we get to each item? We're not using the get method. We're just directly traveling through the nodes. So that means it takes O of n time. Okay. What's cool about this one is, if you might have figured out that I'm a big fan of sorted linked lists. So that's a hint, hint, nudge, nudge, wink, wink for the actual exam. So what's cool about this is, we'll learn this later, is that this is this is the secondary, that merge is the second step in merge sort, and merge sort is super efficient when you're using linked lists. Now this is one of those cases, to address your question, by the way, earlier. It says list A and list B over here, even though I say linked list over here. This is literally just a formatting thing because I don't have enough room to put linked list on, label linked list on the entire top line. So, but they're sorted linked lists, and assume they're linked lists. And now it's a static method, so you don't have access to the nodes. And you're allowed to remove items from list A and list B. Okay, so that's the kicker here. Now what's cool is that, so basically the problem is, given these two sorted lists, we want to take them and make them one total linked list. Linked list, integer out is equal to new. And if you feel like your hand's cramping, it's perfectly fine to say linked list integer out is equal to new LL, you know, or something like that. You're allowed to use shorthand when hand cramps are a factor. What's cool about this, and let's just kind of draw an example here. You don't even give me erasers, for the love of God. Yeah, it's rad. It's what washer machines are for. Okay. So next is the so let's take a look at basically a sort of linked list of 3 numbers: 1, 4, 5, and 2, 3, 7, and let's go with 8. Okay, single-digit numbers, because that way we're not going to get into any confusion later. We want to merge them all into one linked list. There are n total items, by the way, right? So, you know, we could just kind of tack this together and tack this together and sort it, but honestly, that's meh. I mean, right? So one possible solution is the dumb solution, which, yeah, that's what I was about to do. So dumb solution that works because I didn't put any constraints on this. Out.addAll, list A, out.addAll. list B collections dot sort out, return out, and I'll glare at you and I'll go, I guess that's right, fine. By the way, what would the big O runtime of that be? It would be n log n, which we really haven't learned yet, but sorting, when you call collections.sort, it's generally n log n. Although, if that's true for linked lists, I'm not particularly sure. I would assume so. It would just use merge sort for linked lists. But if we wanted to actually sort it manually, it's actually pretty cool. What we can do is that we know that the smallest item is always going to be at the head of one of the linked lists. Always. So it's just a matter of figuring out which one it is. So, 1 versus 2, which is smaller? 1. So cross it off, add it to out. And now repeat. 4 versus 2, what is smaller? What is smaller? 4 or 3? 3 is smaller. 4 is smaller than 5. Sorry, 4 is smaller than 7. 5 is smaller than 7. And then it's empty, so we can just simply add the rest on. 7, 8. And that takes O of n time. Because all we're doing is removing from the head, checking the head, and adding to the tail. So all that we have to do there is while list A is greater, and this is actually how merge sort works. While list A is greater than 0, while list A dot size is greater than 0, and list B dot size is greater than 0. Basically, while both these things have items in it, if list A dot get 0 is greater than list B dot get 0, and I'm able to do the greater than less than, of course, because they're integers. So if A is actually we're looking for the smaller one, so there we go. If it's less than, then we'll just simply say out.add list A.remove 0, constant time, constant time, constant time, right? Those are all constant time operations because these are linked lists. Whenever the get operation, you might throw you like, get is O of n. Well, no, when you're adding to the head or tail, when you're messing with the head or tail, it's constant time, which is great. So the else operation is just simply add from B instead. You're perfectly allowed to do that on an exam, right? If it's the same thing, right? Or you could just, but notice that it took basically the same number of characters. So another thing you might decide to do is, no, actually, let's just do it. So list B dot remove, and we just keep doing that until one of them is empty, right? And then now that they're both empty, we can do out dot add all list A, which will add everything from list A. If there's nothing left in list A, adds nothing. Add all list B will add everything from list B. What's great is that we know that those are the biggest items, and the biggest items are already sorted, and we can just tack them on to the end. If you forget about the add all method, you can just simply go, while list A is not empty, take the first thing in list A and add it to the end of out. And then do the same for list B. Just takes twice as many lines to do as this. Return out. And again, this takes O of n time. That is a... Okay. Yes?
So the add all doesn't contribute to the runtime?
The add all takes...
Or is it minimal?
It's minimal because whatever number of items are left, that's how many it will take. Okay. And add all actually is... Also, add all for a linked list is like really easy. So, because you essentially just adjust where the tail is and just say the tail is now connected to the head. Optimally, for linked lists, add all should just take it takes constant time. Yes?
You also said the get method for a linked list is like
if you're doing the head or the tail, if you have a head pointer or tail pointer, and I would hope to God that Java's built-in version has a head or tail pointer because it.
But that's only if you have the tail pointer. Like if you do get size or like.
Well, if you say get size -1,
Yeah.
we'll get. It would probably say, hey, if I'm looking for the tail, get the tail. There are some optimizations we could put in that we haven't.
Okay.
But right now, all we were doing was getting from the head. Right, there are optimizations you can put into a linked list that we didn't because time constraints and stuff. Oh, this is a pain. Write a method that reverses a double linked list. This method will be an instance method for linked list, so you can use the nodes head and tail references and use the linked list. Ugh, hate this one. Because I always forget how I did this. All right, so reverse. So what we're going to want to, so unfortunately it's not as simple as saying, you know, head is equal to tail, tail is equal to head. It's unfortunately not as simple as that because we also have to reverse the pointers themselves so that what was pointing to the end is now pointing to the beginning. Fortunately, because it's a linked list, it's not too bad, I think. So let's see. There are a couple things we can do. I think we can do node E. Let's see. I think we should be able to do a node E current is equal to the head. Right. And then let's see. And then just try to write it generically. While current is not equal to null, let's see. Current is equal to, so first off we'd have to say current.next let's go with, so let's say next is, so what we'll need is we're going to need to save the next node. Node E, and I'm going to call it after. Node E after is equal to current.next. Okay? And then what we're going to say is current.next is equal to current.prev. So what that's going to do is that's going to, we've got a node. We've saved this guy over here. So what we're going to say is current.next is, that's actually going to point to this guy. And now and then I'm going to say current.prev is equal to is equal to after, so that and that should swap them. I'm still pointing to everything I need to. Nothing's getting dropped at any point. Yes?
Should we start that at the head or the tail? Do you want to reverse it?
Why?
Is it a circular like this?
No? Okay. So the next thing is that normally to advance I would go current is equal to current dot next, but that would make me go reverse, right? That would go.
I'm just confused about the after.
Yeah. So the after is basically after is
Like if you say after equals current.next, isn't that going to try to point to whatever's before head?
So what I'm trying to do is, so I've got this guy. Let's draw what I've got now. So I've got next prev, next prev, next prev, okay? So I'm here at the head. It's current right now. Current.next, so now after is equal to current.next. So after, okay? So let's draw it. After, so I've saved after, which is what's important, because now once I'm done, current will become after, once I get to the end, and I'll be able to advance over here, so I'm at the next node, and then it'll keep chasing along like that, but let's see what happens to the pointers, okay? So current after goes at current, the label after gets applied to current.next. Next we say current.next is equal to current.previous. So that's going to point to null.
Okay.
Now current.previous is going to point to after. Okay? And now we advance. After goes away. After is equal to current.next. And his guys are still there, so let's see. Current.next is equal to current. So current.next is equal to current.previous. And then current.next is equal to after. So it gets kind of twisted up, but that's fine. If you were to actually pull this and rearrange it, it would get in reverse. And then once we're at the end, we just simply say, we just do a, node temp is equal to tail. Let's see. Head is, tail is equal to head, and head is equal to temp, and that would swap all of them. It's much more of a pain to do it with a circular linked list, by the way. Sorry, not with a circular, with the singly linked list. It's possible to do it in place. And of course I completely neglected the simplest solution, which is just simply add everything into a linked list, a new linked list, and then add it back out. So the simplest solution, again, with linked lists, is to do the following. So linked list e temp is equal to new linked list while this dot size is greater than zero, temp dot add this dot remove and then we do while temp dot size is greater than 0, we do this dot add, and then we say index 0 temp dot remove, which will add it but in reverse. This is actually a famous interview problem that you're supposed to solve over the course of 45 minutes, and it basically, this is generally the first solution that people come up with. And then the next iteration of the problem is, well, now what if you can't use a temporary data structure? What if you can't use another linked list to store your stuff? And then the final step is, well, what if it's not a doubly linked list? What if it's a singly linked list? And to solve it as a singly linked list, which I'm not going to go over right now, and that might be a challenge for another day, hint, hint, nudge, nudge, wink, wink, is that what you want to do is that you want to use 3. Basically, you need to use a combination of, I think, 3 pointers to figure out where, to keep track of where you are. It's a very famous problem, so if you were to look it up, you'd be able to find it. All right. Good. So I'm sorry if I'm going a bit quick, but I just wanted to make sure I had plenty of time. All right. Suppose we had a new type of linked list called sorted linked list, which is a linked list but keeps all the items sorted. In other words, if I were to automatically add an item 4 to this thing, it would automatically add the 4 to the linked list so as it remains sorted. Right? You don't provide an index. It just automatically figures out where it's supposed to be. Did everybody understand from the write-up I did there? Right, what the role of a sorted linked list is? You don't provide an index, you just add. So for simplicity, we can do either a singly or a linked list or a doubly linked list. I'm going to go with singly because that's less writing. All right, you can use the less than, greater than sign or equal to sign to compare items, but if you remember how to use compare to, you can do so for extra credit. You can't use the add method. You may not use the get node method, although you can rewrite it. You don't really need it. That's kind of my hint saying you don't need to use the get node method for here. You can't add to a specific index because you don't need it. And the solution must run in O of n time, which is kind of the tricky bit, I think, for a lot of students. But basically, that just means you've got to iterate through the list and find it. Now, key thing to note is that I'm not asking you to sort a list in O of n time. I'm asking you to add an item to an already sorted list. And if it's already sorted, then basically we can kind of figure out a couple different things. First off, let's just compare this to all right, so let's just, again, use a singly linked list with no tail for simplicity's sake, because that gives us the least number of conditions normally, right? That normally has 3 conditions. That would normally be index out of bounds. Don't have to worry about that, though, because there is no index here. So that's awesome. Second, adding an item. So actually, though, there are 3 items, right? Or there's 3 conditions here. One, if I'm adding the first thing ever to this, right? Second is if I'm replacing the new head. If I'm adding a new head to this list, the new head would, and the only way I can know if I'm adding a new head is not adding the index 0, but adding something that's smaller than everything else. And the other condition is adding something that is anywhere else in the list. And the point at which I know when to stop is when the next item is once the next item is bigger than me, that's when I need to stop.
Is that a condition for adding the last item?
Only if I'm keeping track of the tail. But if I'm adding to the last item, if the item is bigger than me, so we can tack that in. If the item is bigger than me at the end, so if the next item is bigger than me or there's no next item, then I just need to add anywhere else. So we'll try our best to put that in. I mean, there's different ways. There's a lot of different ways to actually do this one, which is why I like it. But they still boil down very similarly. So public void e items. So let's go ahead and add our first condition, which is basically, first off, so let's go ahead. There's no need to check for a out of bounds error, but what we do, so we're just going to go ahead and create node adding is equal to new node. Oh, we already know that it's going to be, and it's going to be e, but we are going to use less than or greater than, just for the speed, right? And also because I don't expect you, I didn't really teach compare to yet, so. Node e item. Okay. So, first off, if head equals null, if there's nothing already there, then because the next check I'm going to do is if it's currently less than head, right? It's currently less than the item in head. And if I try to do that while head is null, that's a null pointer exception. So if head is equal to null, head is equal to adding. Throw size plus plus over here at the end. Else if adding is, it's not adding, but item is less than head dot item. And then our last condition is going to be an else, so we'll figure out what goes there in a bit. This, as I would rate it, this is what, a 15-point question? 3 points for this one, 3 points for this condition, 3 points for this condition, and then the rest of the problem gets the 9 points. So head, item, let's see. So if that's the case, then adding dot next is equal to head is equal to adding. It's just a standard attachment over there. Otherwise, I'm going to start needing to do the whole current is equal to current dot next thing to check. Otherwise, there we go. While current dot next So normally we do while current is not equal to 0. Sorry, while current is not equal to null. But if I do while current.next is not equal to null, then I don't have to worry about checking. It actually gets interesting over here. So I'm doing it like this because I've already checked head, which means if, sorry, I didn't declare current. Node, getting ahead of myself here. Node current is equal to head. While current.next is not equal to null, rather than current is not equal to null. And the reason I'm going to do that is I've already checked what current is, right? I've already checked item against head.item. So what I care about is the next one. So while current.next is equal to null, is not equal to null. So then remember to advance it. Current is equal to current.next. Okay. Let's see. So now we want to do is simply say, hey, if current, so there's where I am, and where I am, because I start at head, I already know that where I am is less than or equal to me, okay? And I want to add once I am less than something else. So if current dot next dot item, so if item is less than current dot next dot item, so I'm checking the next item. This will not result in a null pointer exception because I already know that next already exists. But if current.next is equal to item, then what I want to do is, congratulations, attach the node. Adding is equal to current dot, I'll draw this out because I've worked with linked lists enough that I can draw these things in my head at this point. But that's, again, I don't expect most programmers to do that. I think that's a symptom of me being a data structures professor too long. It's more than a testament to my programming ability, which is actually quite laughable. So adding is equal to adding dot next is equal to current dot next, and then current dot next is equal to adding. And then we should probably stop this loop at this point. Break. I could, but I've got my size plus plus over here. Okay. So let's go through, and this should work. Oh, and if current is equal to current.next, and now we need to just. And now we have to figure out what if the item was bigger than everything else, which is if current dot next is equal to null, current.next is equal to adding, and that will attach it to the end. So that's a lot of code right there, but then again, I don't make things worth 15 points for just giggles and other things. So let's go ahead and once again ruin a perfectly good $20 sweater. These things are, I've always looked for another one, but Costco hasn't sold them in like 3 years. Okay. So, all right, so not even gonna bother drawing boxes. 1, 3, 5, 7. So let's go ahead and add 4. Okay, let's go ahead and add 4 to this. First condition is if head is equal to null. It's not. If item is less than head.item. It's not. So current is equal to head, while current.next is not equal to null. If item, which is again we're adding 4, if 4 is less than current.next.item, is that the case? No. So advance. Current is equal to current.next. So current item is equal to current dot next. So if item is less than current dot next dot item, which it is in this case, what do? We do adding dot next is equal to current dot next, and current dot next is equal to adding. So it adds in, just like that. And then we break out of this, and then we ask, hey, is current dot next null? Well, that was our condition, basically, just in case we need to add to the end. So let's go ahead and see what happens there if we're adding 8, just to check this out. We're adding 8, we go current, 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 current. So we advance here, we ask, is current dot next null? Yes, it is. So if current dot next is equal to null, we say current dot next is equal to adding, so we say, so then we would attach 8 there, so that works. There's a lot of different ways to do this one. But generally you come down to 3 cases. Also, I went ahead and kind of just, and you might ask, well, what about duplicate items? I just treated them as, again, my internal assumption was, what if they're less than? All right.
Wait, can you go back a bit? Does that work if you're adding to the second to last?
If I'm adding to the second to last guy, yeah, sure. Because what I'm saying is, because when current is always an item I have checked the value of. Current dot next is the item I haven't checked the value of. Does that make sense?
Yeah, I'm just wondering if it'll add twice.
If it will add twice, no, because fortunately no, because of this break over here, because the break will keep it from getting there. I got lucky there,
Yeah.
but you did have but that was a very valid point there. I'm not immune to mistakes. I make mistakes a lot. I just happen to have made them all a lot of times, so I know how to avoid a lot of them. By the way, if you check the last semester's summary of this practice exam, I probably solved this one in a vastly different way. Guarantee it. Also, me from 3 months ago was probably an idiot, so you shouldn't listen to him. All right, analysis. So this practice question is always on the practice exam, and its corresponding question is always on the actual exam, which is pretty much the same thing. A linked list can be implemented in a number of ways. Compare and contrast an array list and linked list, and I'll be so kind as to tell you the actual problem on the exam worth 20 points right now, which is that a list can be implemented in a number of ways. Compare it and contrast an array list with a linked list using under the following aspects: memory usage, adding and removing items from the list, and getting and setting items in the list. And then I have a nice A, B, and C for you split up so that you can keep it organized. So, going over that, by the way, might as well pull up the nice write-up I did at some point for this guy. So, add and remove is a bit of a pain, but basically, for array lists, this is a bit more detail than you probably need to go into, but it is 20 points, so might as well do some detail. The main thing I look for this question is that array lists in general take O of n time. Basically, the words I'm looking for, it takes this time, except when this happens. So with array list, it takes O of n time to add to an array list, because you have to shift the items. Now, the only exception to this case is, and by the way, I'm video recording this, should upload it today, so you know. The only exception to adding and removing it is when you're adding it to the end, which takes constant time. Now, if you know the word amortized, you can write, if you add it to the end, it takes constant time amortized, and you're done. But if you don't know the magic word amortized, which means on average between a whole lot of runs, then you want to mention about reallocating. And specifically, you want to use the word amortized because that word is magic. It's a magic math word. But in reality, you should probably not rely on magic math words, and instead, right, well, the only other case is when we want to reallocate, in which case it takes O of n regardless of where you add it, including to the end, right? Linked lists, constant time in general, if you've got the pointer, such as the head or tail, or you've iterated somewhere and you've kept it for a lot, for a bunch of operations. But if you don't know where you want to add it to, you got to find where you want to add it to, which takes O of n time. Getting and setting, array list is as easy as can be. That should be the easiest point you ever make, which is that it takes O of n time to get and set on an array list. For a linked list, it takes constant time for get and setting. Constant time for getting and setting on an array list. For a linked list, it takes O of n time, unless, of course, you have a pointer to it, in which case it takes constant time, right? The rule for linked lists is that if you got a pointer, it's constant time. If you have to search for it, it takes O of n time. The linked lists are good at what array lists are terrible at, and array lists are terrible at what linked lists are good at. Just remember that. Okay. And we've kind of talked about memory usage. Array lists can waste memory by reallocating, right? Array lists can waste memory by reallocating. However, if you are kind of clever and decide to look up something, let's go with the array list. So let's look at the array list docs in Java for just a second here. And you'll find that there's a lot more methods than I actually bothered writing because there's way too many of them to, do in a reasonable amount of time. Notice that first off, if you know the capacity of an array list that you're going to fill up, you can set the initial capacity, right? If you don't, the initial capacity is 10. That's cool to know. But say you're going to be filling up your array list with 1,000 items. Then you just declare 1,000 there. Guess what? You never have to reallocate, ever. Clear removes all items from the list. Ensure capacity increases the capacity of the array list to ensure, if necessary, to ensure that it can hold at least the number of items specified by this. So if you enter in 1,000 as capacity 500, it will increase it to 1,000 right then and there. If, on the other hand, you enter 500 and its capacity is currently 1,000, it's just going to go, yeah, we're good. We can hold 500 items. Trust me. I think I'm looking for trim. Yep, trim to size. And finally, there's trim to size, which trims the capacity of the array list down to the size of the actual list. So basically, it makes the capacity and size match. Takes O of n time, but now you're no longer wasting memory. So array lists, they use less. They don't have as much overhead as linked lists, as we'll see. But they can waste memory. But if you're clever, you can prevent it from wasting memory. The answer I'm just looking for, by the way, on the exam is that they can waste memory. And how can they waste memory? From reallocating. With linked lists, on the other hand, each node, right? So an array list, you've got, right? Basically, you've got E item, which is a reference to an item, right? Each slot in an array list has E item, some other E item, right, and so on and so forth, right? And each item in there is actually not the item itself, it's the memory location of that item because they're objects. So, and when you're dealing with objects, there's just no way to get around that. On the other hand, if we are dealing with linked lists, right, you've got not only the E item, but you've got the next pointer as well. And if you're using a doubly linked list, you've got the previous as well. So it takes much more overhead to do that, right? It takes about, by the way, each of these, the cost of each of these to store these in memory is about an int. This is about an int's worth of space, an int's worth of space. So you're using about up to twice or 3 times as much overhead as an array list. But you have no need to trim. The size expands to when you want. The idea is that you want to use a linked list. What situations would you want to use them? You want to use a linked list when you know you're going to be splitting it up a lot, or shuffling items inside around a lot, or iterate or adding to the head and tail a lot. Otherwise, use an array list. However, if you know you're going to be inserting into the middle a whole lot and shifting stuff over, and it's not a great time to use an array list. All right. Also note, because I don't think I mentioned this earlier. Oh, no, I didn't. So on the practice exam, there were 100 points. Right? On the practice exam, there were 100 points. On the actual exam, oh, good. There's 105. On the practice exam, there's 105 points. On the actual exam, there's going to be 105 points. You're graded out of 100. So there's a 5-point buffer built in, kind of a 5-point automatic curve there. So that also does mean you can get over 100 on the exam, which is great, and gnarly if you need to. That's the case for both of the exams, the first one and the second one. Not the case for the final, because for some reason, because I don't know if I could get the other professors to go along with that. So yeah. Anyway, so that's what I've got for you today. Good luck on the exam. I've got to go and get them printed now, so.